Hi everyone, welcome to our YouTube channel, Becoming a ROS Developer here at The Construct. My name is Rodrigo, and today we're going to have a student presentation for one of the projects that we have for our ROS Navigation in 5 days course, in which Morteza is going to show us how he did this project, and he's going to show us how he made a Turtlebot here in our offices autonomously navigate. So welcome, Morteza. Thank you for spending time with us and doing our project. How are you doing?
Hello, and hello to you and everyone who watches this. I'm happy to be here again, and this is my second presentation, and I'm happy.
Great, great. So yeah, you also did the ROS Basics course and presentation, so congratulations for that. And so yeah, let's just, without further ado, just get started. So if you want to share your screen and just show us your project,
Okay. Well, do you have my screen?
Yes, we can see it.
Okay. So let me just say quickly that in this project, first I've created a map of the environment, and then I used localization package AMCL to simultaneously localize the robot in the environment and in the created map. And after that, I'm trying to save a few locations in the map and then move the robot autonomously uh, to those locations by calling my service. So that's the short story of what I'm going to do. So this is the environment of the map. As you can see, this is the real robot lab, and this is RVs. I've called RVs before. So as you see in this picture, I've launched my localization map, my AMCL launch file. So you can see the particle cloud in the environment. These are the points that the robot may be in that code. So I'm going to disperse the cloud points all in the map, so my localization become more accurate. So I'm calling ROS service global localization with no inputs. By calling this service, as you can see, the cloud point dispersed all in the map. So now I'm starting to move the robot. So the location of the robot becomes more accurate as the robot moves in the environment. For example, I made the robot rotate a circle, one round. So as the robot gets its laser readings, and by the computation of the AMCL, it changed the probability of its location in the cloud points. So some of the points get more probability that the robot is occupying that location. So let's move the robot a little further more. As you can see now, the robot is approximately in the right position in the map,
Yeah,
in the
it's
correct
almost
position in the
localized.
map.
Yeah, yeah.
Yes, almost localized.
We have an issue with this Mac specifically because I think how symmetrical it is, it makes it harder for
Yes,
people to
exactly.
localize.
So I'm going to go to the next step, if you agree.
Yes.
Okay. Uh, Now the robot has its position in the AMCL post topic. So I'm going to run a node that I've written before to save some of these locations in a YAML file.
Okay.
So I'm going to run. Uh, yeah, the name of the file is spots to file.
Mm.
So by running this node, a service server becomes active. And for example, let's move the robot to this position. Okay. Now I'm calling that service. The service name is save spot, and it takes one input, which is the name of the label of that coordinates. So I just name it C1, for example.
So that is when you run this node, you are saving the position where the robot is currently at.
Yes, the position and orientation of the robot where currently is. So for example, this location, we called it C1. We add this label C1 to that file.
Oh, I
So
understand.
let's move the robot to another point. Okay. Let's save this spot too. We call it, for example, C2. Okay, and move further. Oh, I didn't see that pedestrian.
Maybe with a person detector
Yeah,
node for your next project.
that would be great. Okay, let's call this C3. Okay, now I'm going to change the robot's position. Why the robot doesn't move?
Did it stop moving?
Yeah.
Huh.
Okay, let me.
Do you get your topics?
No, I'm getting no topics,
That's
unfortunately.
strange.
I think the connection may be.
Well, I can see it move it now.
Eh, I'm not moving it right now.
You're not moving this?
Not right now.
Well, this is a first. It looks like it's moving on its own.
Or maybe it has some latenance. I don't know.
No, because that's as if someone else was moving it. So, do you mind? Let's see. Let's think of. Do you mind disconnecting from the robot and connecting again?
Okay.
You got still 50 minutes left in your reservation, so
Okay, let me disconnect. Okay.
Okay, and then we can try and connect again.
Do you see the error?
Yeah, I can see that.
It's look like someone else having the session.
It looks like, yeah, maybe someone is interfering. That's very strange. It's never happened. Um, give me 1 second to check if there's two names or something that someone else might have reserved it on accident, but I don't think
Okay,
that's possible. Give me just a minute or two and I'll be back.
that's
Okay.
okay. No problem.
Hi, Morteza.
Hi.
I am back. So, yes, it looks like somehow there was another username register at the same time, even though your reservation was in place. So, anyways, I erased it. So we should be able to do the whole thing again.
Okay.
I assume. Sorry about that.
It's okay.
Hopefully this time no ghosts will control the robot.
Okay, I'm going to launch the localization package again.
Mm-hmm. All right, that means we did get some data.
Yeah. Uh,
So you're going to do that the same, spread the particles around to be able to
yeah.
localize it quicker. And I've realized that if you rotate it only, it's the same as you were moving back and forth. So usually I just start rotating it around, and it's
Yeah,
probably the quickest way.
it's better. Let me go a little further.
Mm-hmm.
Don't collide with the walls. I think it couldn't locate accurately until now. So let me just move it a little more.
Oh yeah, I think it's thinking it's on the opposite side. Yeah,
Because it's a little, as you
symmetrical.
said, it's
Yeah.
symmetrical. Yeah. think here is better. Okay, let me rotate it again.
It looks like those particles are trying to converge
Okay,
to either the one
uh,
side or the other.
because we have uh, done this stage, are you agree that we use 2D pose state
Yes, absolutely.
estimator just to speed up
Exactly. So now it kind of knows where it's
everything?
at.
Yeah, let's do another turn.
Okay, now it's converging in the on the right side. Good.
Yes. Okay. Unfortunately, my screen is a little small, so
Yeah.
I have a little trouble seeing all the pages, all the screens. So let me go in that position. Okay, now I'm going to run that service to save robots spots.
Mm-hmm. If you want, you can just do one to
Okay,
save
just one.
time, and we can move it to another location and try with what that one point.
Okay, I activated the server.
That's a service server, right?
Yes, yes. Now I'm calling it. Okay, with label C1. Okay, now I'm, for example, coming a little, changing the position of the robot,
Mm-hmm.
and now I'm calling the server service with the end label. So when we give the label end as label, the service knows that it has to save the
Oh.
files and terminate the file. So now our file is completed, our YAML file, which holds the position of the robot in
Mm.
C1.
Mm.
So now we are going to activate the, let me cancel this service. Okay. Now we are going to activate move base. So ROS launch my path planning and move this. Okay. As a core functionality to be able to move robot autonomously.
Right.
So we wait until the node is activated completely. Yes. Now we see the different map cost maps, local and global cost maps,
Oh
and
yeah, I see that.
we have them on the R list. So I'm going to call another service which uh, we we can call our saved labels, for example, C1, and the robot goes autonomously to that spot.
Mm. Okay.
So uh, launch. We are activating the service server, navigation service server. Okay, and now we're calling that service. The name of the service was get coordinates. get coordinates. So as you can see, the input of the service or the goal variable is labeled. Now we are inputting C1, and as you can see, the robot plans its path autonomously and moves to that node.
Oh, nice.
And we have the message that it was successful.
So it's loading the YAM file that you saved
Yeah.
just now and uses those coordinates to send to move base. Is that correct?
Yes, that's great. After we save the uh, location of the robot in the YAML file, we call this service that by getting the label, it reads the coordinates of that label and moves the robot autonomously to that location.
Oh, great. And but in here from Arviz, you could still give it a different navigation goal, right? So from here,
Yes,
if you click on, let's say, the other corner, will it try?
yes,
Oh, there we go. Nice. So and it looks like the tuning of your AMCL. I'm sorry, your
move
move
base.
based parameters are quite right because it's always, especially in small environments like this, it makes it so hard for the move base to find the goal and
Yes.
to so good
Well,
job there.
it took a lot of time.
Yeah, I bet.
So you can see the spots file here. It is the YAML file that we save the
That
location
it's
of the robot.
generated. Okay.
So if there is any question, or should I explain?
I mean, it's first of all amazing presentation. Sorry about this little issue here, but if you want, you can either you can just start showing us each your code
Okay.
and how you did all these things. Now that we saw that it does what the project asked.
Yes.
Yeah.
Okay. The first part of the project was mapping.
Mm-hmm.
So by the use of the G mapping, uh, okay. Okay. As you can see, this is a stamp G mapping node launch file that uh, runs the stamp G mapping node of ROS. So, and we have here different parameters such as the scan topic, base frame of the robot, and the ODOM name frame of the robot, and different settings, for example, relating to the laser range and other things. So after we run this launch file, SLAM-G mapping, and move the robot around the environment, the map becomes complete, and we can save the map by map saver package. So
Yes, it's a. I know what you're trying to say. That it's a saved command available for if you install ROS. It's a package that comes installed, and I think is ROS run map server map saver, and it.
by completing the map by SLAM-G mapping, the map topics becomes complete and more accurate,
Mhm.
and the map saver package saves that topic into a map, so we can provide that map to any other launch file or any other node by calling the map server
Mhm.
node of the map server package. So this is a launch file that calls that map server node, and it has one argument, which is the path or directory of the map we have saved. For example, here we saved the map in the Turtlebot mapping package
Mm.
in the map directory. So you can see here the two files related to them, my map underlined one map. So after we shut down the mapping, we are going to use localization package. As you can see here, first uh, we launched the provide map launch file. So our save map becomes active. So we have the information of the map in the topic of the map. And by the use of that information, AMCL localization, Monte Carlo localization package can localize the robot in that map. As you have seen, it uses a cloud point particle set of points in the environment as a guess of the robot's location.
Hmm.
And by moving the robot, the probability of those points changes. And as robot moves around the environment, uh, it gets more accurate. So it has the best accurate position in the AMCL pose topic.
Hmm.
So after the robot finds its location in the map, we can use move base to autonomously localize the robot in the map. The move base uses two maps, global map and local map.
Hmm.
That these maps includes different information about the obstacles in the environment and the inflation of those obstacles in the map.
What do you mean by inflation?
It's kind of like, as I understood, it's like a safety distance, for example. Uh, we enlarge the obstacles uh, to create a safety and
Yeah,
to consider robots geometry.
exactly. It's because of the robot's
Yeah,
size,
it's not a
because
point.
it's not a point, it has a certain diameter, so those that inflation layer protects, yes, makes the obstacles bigger so the robot cannot crash against it with the edge. Yes,
Exactly.
nice.
So here in this launch file, we call the move base launch file. As you can see, has several config information files. So one of the important part of the project was to arrange and change these parameters and adjust these parameters so the robot could move uh, correctly and autonomously in the environment.
Mm-hmm.
There are five important parameter files: common cost map, uh, local cost map, global cost map, and the move base and local global planner and local planner. Each of these YAML files are contain information about the behavior of the nodes of the autonomous navigation nodes. For example, in the let me see. For example, here we have the inflation radius that we can adjust.
Mm-hmm.
And here we have three plugins related to obstacles and inflation layer and static map information.
Mm-hmm.
So let me find the, uh, this is the information about the robot's geometry, the footprint of the robots. So as the robot gets bigger, uh, it should consider, for example, moving and turning may conclude in moving to obstacles.
Mm.
So this is important to adjust. And uh, let me explain the save to spots to file node. As you have seen, by calling this node, this is a service server node that when we call this, it saves the robot's location under a label. So as you can see, this is the callback
So you're
service.
you subscribe to the AMCL pose. So it's the pose that the AMCL node is publishing. Then it's not like the odometry or something.
Yeah. It's created by the AMCL
I see.
package. Yes, and so we save the pose of the robot, position of the robot in this callback, this topic callback, and in the service callback, uh, we uh, we read the label that's requested, and we save the uh, save the location of the robot in the YAML file. So until we have the end label. After the user inputs the end, the YAML file becomes complete, and as you can see here, we have the message that spots is created.
Right. Okay. Nice. So
So
technically, you could add an infinite amount of points for your map if you had a big map, correct?
yes, until the user terminates the service.
Right. Okay.
So as you can see here, add to spots. Let me. Uh, this is the function that reads the position and orientation of the robot, and it creates a dictionary containing position and orientation keys, and it adds every label's information to this dictionary.
Mm.
So at the end, by calling the end label, this dictionary is dumped or write into a YAML file. So after we have the YAML file containing the information of the robot's locations, we we call the service get coordinates. Well, let me just say this before. In
Yeah.
the navigation launch file that we call, first we load that YAML file containing the information of the position of the robot.
Mm.
So after we load that file in the rasparam space, we are calling the service server, get coordinate service server.
Right.
Well, this service, after the service activated, when we call this service with a label, it reads that label's information in that YAML file. So,
Oh.
and yes, please.
No, no, I'm saying
Ah,
that's really clean, really nice.
yes. For example, we had the C1 label. So it reads that parameter in the parameter server, and it writes location, the information on that label, position information on label in the val parameter. So after that, we calling the send coordinates class. So let me just show this. This class uh, has two inputs, val and label. So after the get coordinate service server reads the information of that label and uh, creates the val variable, it creates a variable of the type. Let me find it. I'm sorry. Of the post type. So
Mm.
yes, and we complete this variable. For example, its position XYZ, orientation XYZW, and after we complete this variable, we give we send this variable as a goal variable to the
To move
move
base.
base move base service. So, and the move base tries to autonomously navigate to that point. I'm sorry if it wasn't very, I couldn't very explain it really well and good.
I think you explained it quite fine, so don't worry.
It was about the English, not about the
Oh, don't
knowledge.
no issues there either. So don't worry.
Okay, if you have any question, I
Yeah.
would be happy.
Do you mind stopping sharing your screen?
Yeah, yeah.
Okay, let me just. All right. Yeah. So, wow. Congratulations, Morteza. It's a really, really cool project. This is actually our first complete project for navigation. So it's really
Thank you.
exciting to see that it worked so well. Um,
Thank
and
you. It was really exciting working on it.
Oh, that's great. That's what we want. So you get the experience of actually knowing that your programs are making it navigate autonomously. So congratulations. I really liked how easy it was to understand the structure of your program. I really liked how you put all your parameters separately. This is important because if you are trying to debug just one config file, it becomes a nightmare. And separating it is just really important and really good practice. And I also really liked um, the fact that you could save an infinite amount of points. And so I just wanted to say, just congratulations. It's really, really impressive. I do have a couple of questions, if you don't mind. Um,
Okay, yes.
so first of all, going through this project, what are the most important parameters or the ones that gave you the most trouble that you had to spend the most time tuning or changing?
Well, the most, I think, challenging part of the project was to adjusting the config files for the my move launch file, my move base.
For move base.
So yeah, including the common cost map, global cost map, local cost map, and global and local planners. So, for example, I didn't know exactly about the inflation layer variable parameter.
Mm-hmm.
So uh, after I created the map and the AMCL was running correctly, I couldn't navigate the robot autonomously because the inflation layer was very big and almost all of the environment was known as obstacles.
Right. Yeah. Yeah. So
The
that was the toughest one, you'd say, the
one
inflation
of
layer.
the yes. So for example, adjusting the base footprint of the robot was very important, and
Oh yeah, I noticed that. Is there a particular reason why you used the frame base footprint and not base link? It's the same thing, except I think base footprint is right against the bottom of the robot, and base link
yes.
not. Is there a reason why? Did it not
Well,
work with base link, or you just?
sometimes they're both have the same information, and
Mm-hmm.
but sometimes not.
Yes, that's
So
correct.
yes, so if if you see the uh, information tree of the uh, TF tree, for
Mm.
example, yes, the first one is base footprint, I
So you
think.
went with the first one, yeah.
Yes.
That's a good way to do it. And let me ask you, doing this program that saves the spots, and then you can later use that other server to make it go to those spots. Do you think what use cases, what specific thing, like practical
Mm.
stuff, do you think you could do with this? Is there? I'm thinking like if you were to create your own robot and use this for a certain application, is there
I
something you
think,
can think of that would be really useful to use something like
yeah,
this?
two case comes to my mind. First is in smart or autonomous warehouses, so in which there are a lot of robots moving autonomously from point to points, for example, to pick some goods and transfer it to another place, or any autonomous logistic applications, for example. And another is in services, for example, like in restaurants or in common places where what do you call it?
The waiters,
Uh,
the robot waiters. Is
yeah,
that what you're talking about?
yeah,
Yeah.
kind of, yeah.
Yeah, that is exactly what I was trying to get at because
Yeah.
this is exactly, I mean, I don't know if they use ROS or not. I've only been to a couple of restaurants that they have this robot that brings you the food, but this is exactly what they do in the background. So yeah, yeah, I think that's really,
Yes.
really cool. Um, and yeah, for logistics for the warehouse as well. There is a specific um, extra work that you want to do if you want to do it super precise. Uh,
Yes.
for example, like going to a charging position. For example, we have a warehouse robot lab over here where I created a little program that uh, makes the robot automatically go charge to a charging station. And I discovered that I couldn't just give it the position of the charger because it wouldn't reach it every time. But what I would do is send it close and then use another pure pursuit algorithm to approach it
Yes.
carefully.
Well,
But
yeah.
yeah,
Another challenge is, I think, is working with multi-robot systems. This is what I'm working currently on it. So, for example, multi-robot path planning.
oh yeah, that's really
Yeah.
interesting.
Yes, and I think that's another challenge in those applications.
Definitely, definitely. Um, so I think that's it. That's all the questions that I wrote down. So I just want to congratulate you again
Thank you.
and let us know how that project of multi robot navigation that you're doing and if there's anything interesting. So to keep us posted. Maybe when you're done, we can even do a little demonstration here. So
Sure.
again, congratulations and. For everyone else that's watching, this is what you can do here in our courses after you have taken it and learned good autonomous navigation, and you can show it in a real robot, so you can present that you actually know how to implement these algorithms and use them in real scenarios, like we were talking about for restaurants or warehouses or things like that. So, congratulations, Morteza, and I'll see you again, hopefully very soon.
Thank you. Thank you for this opportunity.
All right. Well, thank you guys. I'll see you guys later. Bye bye.
Goodbye.
All right. Great, Morteza.